Right now, that rover, Perseverance, is 200 million miles away on the surface of Mars. It's on the floor of Jezero Crater, and it's taking the images and collecting the samples that might tell us whether life ever existed on the red planet. Jezero Crater is one of the most important and enigmatic sites in the solar system. Around 3.8 billion years ago, it was filled with a lake. But that lake is long gone. Mars has become a dry and barren world. Today, Perseverance and the Ingenuity helicopter are searching the crater for signs of the life that may once have lived there. What they find could transform our understanding of life on Earth and throughout the universe. It is certainly the most audacious mission ever sent to the surface of another world.
TDL is the mission. I have you 5x5. Help me.
I have you 5x as well.
This is a crucial 7 days for the rover. And I've been given extraordinary access to the Perseverance mission. I'll be following the rover's every move as it attempts to travel further and faster than ever before. Through its cameras, we'll show you what it's like to stand on and explore the surface of another world. This week, we'll see the red planet as no one has seen it before. This is NASA's Jet Propulsion Laboratory, 4800 Oak Grove Drive, Pasadena, California. From the 1960s onwards, it's been the control center for NASA's pioneering deep space missions. And now, it's the headquarters for the hundreds of scientists and engineers who make up the Perseverance team. JPL is a really special place for me because way back in 1980, I wrote to them because I was interested in the exploration of the planets, and they wrote back. This is it. Imagine the excitement when this brown envelope arrived from California, filled with images of the solar system, the moons of Jupiter and the rings of Saturn. I mean, this is one of the reasons that I became a physicist. Well, now, 40 years later, I'm actually at JPL because as I speak, there is a rover roving across the Martian surface, the first mission dedicated to the search for life on Mars. And this week we have unique access, not only to mission control, but also to the navigators who are plotting the path of Perseverance around the boulders and the mountains of Mars. And we're also going to see the photographs, the data come down in real time. We're going to learn things about Mars that nobody has ever known before. Can't wait. Just over a year ago, the world held its breath as the Perseverance rover, the flagship of the Mars 2020 mission, made its final approach towards Mars. After 7 years of development and a 6-month journey, no one knew if the $2.7 billion rover would make it safely onto the surface.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
Since then, Perseverance has been exploring the area around its landing site in Jezero Crater, sending back the most extraordinary images. With the exception of the occasional animation, every image of Mars in this program has been captured by the cameras on Perseverance or the other spacecraft around Mars. Perseverance's mission is to search for signs of long extinct life. What it discovers could answer one of the great existential questions. Are we alone in the universe? This is JPL's Spaceflight Operation Facility, or better, Mission Control. And this room is iconic for anyone that's into spaceflight, because this is the room in which all those dramatic moments that we all remember happened. You know, the dive of Cassini into Saturn, the landing of Curiosity and Perseverance on Mars. They're talking now to the solar system, anything that's out there. And this is where all the data comes down from the Perseverance rover.
TCL conversation is 5
This morning, the crew in Mission Control are waiting to hear from Perseverance, which is currently 200 million miles away on the surface of Mars. To find out how communication works across such vast distances, I've come to see Rick Welsh.
So this room sometimes we call the center of the universe. This is where all the data comes through this facility from all our spacecraft out in the solar system, right? So you can see up on the screen the different antenna. We actually have antennas at 3 locations around the Earth, which allow us to really look out and see spacecraft no matter what planet they happen to be at.
How does that work? Because Mars is, what is it, about 200 million miles away, give or take, at the moment?
Right now, as you said, we're about 300 million kilometers away. And it's probably about 16 minutes to get our signal all the way to Mars, one way. So compare that to the moon, it only takes a couple seconds for a signal to get back and forth to the moon. So even when we had astronauts there, it seemed like we could talk back and forth in real time. 16 minutes is really too long to do any kind of real-time communication.
This delay in communication between Earth and Mars determines so much of how the mission operates. Because the team are unable to control the rover in real time, they must compile detailed sets of instructions to send to Perseverance every day.
So the scientists and engineers here on Earth spend about 8 hours deciding the next things for the rover to do and building the commands. We then send that up in the Martian morning. The rover's on its own to execute those the best it can, and then we hear back in the Martian afternoon what actually happened on Mars.
Oh, so that says next UHF 2 hours. So is that what that means?
That's right. So we're very interested in getting our downlink today to see how the rover's doing, and that will be arriving here in about 2 hours.
While the crew in Mission Control wait, Perseverance is uploading its latest data to one of several spacecraft in orbit around Mars. That spacecraft will relay the data back to Earth in 2 hours' time. This is optimism. Engineers like their acronyms, so that actually stands for Operational Perseverance Twin, for the integration of mechanisms and instruments sent to Mars. But it is, in every important way, an exact engineering replica of Perseverance. There are a few things missing. For instance, on Earth, it's not safe for the rover to be powered by a nuclear battery, so instead, it's plugged into the mains. But for example, it has exactly the same flight computers as Perseverance. So if they want to upload new software, then they upload it to that first and test it to make sure it works. And it's quite an imposing thing, isn't it? It's bigger than I thought. Weighing over a ton on Earth and standing just over 2 meters tall, the rover is a beast. And it's packed with instruments designed to scrutinize the Martian surface. Among them are 19 cameras, more than any other spacecraft. 5 are mounted at the top of the mast to give a human-like eye-level view of the Martian landscape. Lower down, cameras focus on the area in front of the rover, where the robot arm is deployed to study and sample the surface, looking for signs of life. In just over a year, the rover's cameras have sent over 200,000 images back to Earth. This morning, the latest batch of photos are just about to arrive at JPL. And I'm going to look at them with the leader of the science team, Ken Farley.
So here we have one of the images that just came down from Mars today. And it's a great landscape looking off to the north and east in Jezero Crater.
Yeah, and do you still get excited by the idea that nobody's ever seen this planet from this angle before? It's completely new data.
How could you not? I mean, this is just, I love it. It's just every day to be able to take in a landscape like this and be surprised by things that we see. Still exciting to see it every day.
Could you describe what we're seeing in this image?
In the foreground, you see the area that we've been exploring for most of the last year. That's the crater floor. And then the thing that just captures everybody's attention, including mine, is the delta. And the delta is very distinctive, and it's got a flat top. You can see the flat top on the left side.
Yeah.
That's about 40 meters high.
The delta is the most important feature in Jezero Crater. And it's the reason Perseverance was sent here. It was formed at the mouth of a river that flowed into the lake that once filled the crater. The delta's layers of sedimentary rock are thought to be the most likely place to find evidence of the life that may once have lived on Mars. And it's where the rover is headed to next.
We are just about to embark on about a 5-kilometer drive to get to the delta. We would love to just go straight there. It's only about 2 kilometers, 2.5 kilometers as the crow flies. But there are boulders in the foreground, and in the middle distance, as you can't easily see in this image, there are sand dunes. So we have to go all the way around to get there.
You don't want to get stuck.
We absolutely do not want to get stuck.
Basically.
That would be bad.
Well, we've arrived at an extremely exciting time for Perseverance on Mars. For the last year, it's been exploring this region around here, but now it's going to set off to its primary target here in the ancient river delta. Now, it can't, or they don't want to, take the direct route, because that would be through this rocky dune field. It would take a long time, might even be dangerous for the rover. And so what will be happening this week is it's going to head off about, hopefully, 200 or 300 meters a day, driving in this direction. And then by the end of the week, I'm looking forward to this, it's going to thread its way, we think, around the side of this crater. It looks quite nasty from the air, but they say that it's certainly passable. And so if we're lucky, then Perseverance will be around here at the end of our week here at JPL. Over the next week, I'll follow the rover's every move as it starts the most important drive of its mission so far. To cover the 1,200 meters to La Orotava crater in just 7 days, the rover will need to break all distance and driving records. No rover has gone so far across the surface of another planet in such a short space of time. We're hoping that journey will start today, but first we need to be sure the rover is ready to move on.
This is where it happens.
So Rick is taking me to the daily briefing meeting on the rover operations floor.
Coming into the Perseverance operations facility, we have this great selfie of the rover, which is awesome to see. And this picture is actually taken with the camera at the end of the robotic arm. So if you were the rover, it's taking over 50 different pictures to actually build this mosaic.
I remember one of your engineers actually saying that it behaved like one of his teenagers would, because it landed, the first thing it did was it landed and take a
Exactly.
selfie.
Exactly.
This maze of rooms is the beating heart of the mission. It's usually strictly off limits to outsiders. But today, I've been given special clearance to join the team inside.
So this is one of our big operations room. We call this the Mission Support Area, or MSA. And this is where our data comes.
Good morning, Martians. Let's get started with the downlink briefing.
Our tactical downlink lead today is Keith.
Mission, how read? TDL, this is Mission. I have you 5x5. How me?
I have you 5 by as well.
He's actually checking in with all the team members, all our engineering and science members, to make sure they can hear him.
I have you 5 by as well. Supercam, how read?
This is the team's chance to check on the status of the rover. And this morning, it seems all is not well.
So as you may know, we had a fault with the arm when we were trying to do the core. So the arm was left preloaded on the surface. Subsequent to that...
Occasionally we do need to say, well, we see some issue with the system, and so let's preclude use of that for tomorrow until we have more time to look at it.
Yeah, I think he said that the drill is paused.
Monday we'll be looking at the meta in parallel.
Before it's even started its record-breaking drive, the rover is facing a problem that could delay its progress. And it stems from this. The last task in its investigation of the crater floor was to take a rock sample from this boulder, informally known as SID. So what have we got?
This is a very interesting image because we are trying to take a core sample of this rock, and the rock was too hard and the coring faulted. It stopped with the drill still stuck in the rock. It's not supposed to be like that.
I suppose you don't want to break a drill bit, right?
That's exactly right. If the rock is too hard, you start to dull the drill bit. And we have a small number of drill bits, and once they're all dull, we're not going to be collecting any more rocks. So we are very careful not to push the drill too hard.
And while the drill is stuck in the rock, the rover can't go anywhere.
This is what it's like on a rover mission. Every day there's something new that you have to deal with.
So what do?
We're asking for a core that was about 6 centimeters long, and we know it got to 5 centimeters before it faulted. So 5 centimeters, good enough.
Oh, so you don't care about the extra centimeter, you just want to get that core.
And we've decided that the best thing to do was to simply snap off this core from the rock and ingest it into the rover and seal it.
As our first day at JPL ends, the instructions telling the rover to break off the sample and withdraw the drill are sent to the Deep Space Network and onwards to Mars. We won't know if it's been a success until we return. Our fascination with Mars is nothing new.
We know now that in the early years of the 20th century, this world was being watched closely by intelligences greater than man's.
Stories of Martian visitors were once a staple of cinema and radio. And at the time, those stories didn't seem as far-fetched as they do today.
Intellects, vast, cool, and unsympathetic, regarded this earth with envious eyes and slowly and surely drew their plans against us.
It's hard to believe today, but a century ago, actually as recently as the 1930s, it was perfectly respectable to imagine that there was a civilization on Mars.
Invaders from Mars, weird, fantastic beings of a superintelligence, ruling a race of synthetic humans and pitting them against mankind's dream to conquer the universe.
That there were beings as intelligent or even more intelligent than us staring down at Earth.
This could be the beginning of the end for the human race. For what men first thought were meteors or the often ridiculed flying saucers are in reality the flaming vanguard of the invasion from Mars.
Even into the 1950s, it was reasonable to think that Mars was covered in vegetation. And the reason is that until the space age, this was the best photograph we had of Mars. This is from the 100-inch telescope at Mount Wilson. And these dark markings on the surface, which move around actually, or appear to, as the months pass and the seasons change, look for all the world like vegetation. And this is a book written by the great Patrick Moore in the 1950s. It's titled A Guide to Mars, and in the chapter called Life on Mars, Patrick Moore writes this: "To sum up, there is no reason to suppose that low forms of vegetation may not exist on Mars, whilst there is a great deal of evidence that they do." But that changed with the dawn of the space age. In November 1964, NASA launched Mariner 4 towards Mars on a mission to return the first close-up images of the planet.
The spacecraft is flying toward Mars, about to pass within 6,000 miles of its surface.
Back at JPL, they waited anxiously as the data trickled in. This would be the first time we'd seen the surface of another planet, and potentially signs of extraterrestrial life. But all that emerged was a barren, crater-scarred world with no sign of life, and certainly no Martians.
On August 20th, 1975, the first Viking spaceship was launched.
Subsequent missions revealed the planet in greater and greater detail, hinting at a very different past. By the mid-1970s, the Viking missions had discovered great river valleys, proof that large amounts of water had flowed across the Martian surface. To investigate that history of water, a string of rovers were sent to explore the surface. They discovered a very different world to the Mars we see today. There was evidence that in the past, Mars was covered in lakes and even oceans. On Earth, we know that wherever we find water, we find life. This all suggests that even if Mars is a dead world today, it may not always have been so. In just 50 years, we've come full circle. From Mariner 4 apparently suggesting that Mars is a dead world to believing again that it is certainly possible that life may have existed at some point in the history of the Red Planet. And now it's up to Perseverance to see if that's true. Day 2 at JPL, and I return to Mission Control to see the new data that Perseverance has sent back. Cam, so last time we spoke, the drill bit was stuck in a rock. So what happened?
Well, we have this image of a beautiful rock in the drill bit. So now we know, just from this image alone, that the drill was able to break off the rock core and pull out.
So that one's been solved. The sample's safely stowed away. So what's the plan today?
Well, that was the last thing we had to do to complete the Crater Floor campaign. And we are ready to begin the drive campaign. So the main activity for the next few weeks is drive, drive, drive.
With the time lost to the drilling fault, Perseverance will now have to average 200 meters a day if it's to reach La Orotavo crater by the end of the week. But the pictures from its cameras show that it's starting from a tricky position, surrounded by a maze of rocks and sand traps. To find its way onto clearer ground, Perseverance is going to need help. Vandy Verma is head of the rover driving team. Hello, Vandy.
Hi, nice to meet you.
So you're about to set off on the journey, the long journey, around to the Delta. So how do you plan the next route?
So we look at the images. So I would look at these navigation camera images I took in the direction we expect to drive. Let me turn this 3D goggles on. If I put it into stereo so you can yourself see it.
Oh, that really is quite impressive, actually. I can see the surface of Mars coming out from the screen.
And you can see a curved ripple here with the rocks on it. It's a really good substitute for standing where the rover is on Mars and kind of looking out to see how you would navigate the terrain.
Using the 3D images, Vandy can begin to plot Perseverance's route through the obstacles.
Essentially, we are saying we want to navigate around this area. So we are doing the path so it goes around this, but we don't want to go over here because it's very sandy. And sand, actually, the wheels don't do very well. You can see all the layers as you start.
In hazardous terrain like this, the only way the rover can safely find its way is by following Vandy's carefully plotted route. But this mode of rover driving is slow. It's only possible to program around 30 meters of driving each day, nowhere near enough to cover the distances required to reach the Delta. So once the rover reaches safer ground, Vandy points it in the right direction and activates its secret weapon.
So now we're going to turn on AutoNav because the rover will know more on Mars at that point than we know here.
AutoNav allows the rover to drive itself across open terrain where there are fewer obstacles to avoid. Analysing the stereo images from its cameras in real time to pick a route across the surface. For a demonstration of how it works, I'm back in the Mars yard to meet the Perseverance project manager, Jennifer Trosper. So I was told we have to wear these coats. I thought it was for my safety, but I'm told it's for its safety to protect it from me.
It is. Yes, and that's why I'm hooking up right here so that I don't zap any of the electronics.
So if I were to sit here, and I can't believe I'm saying this, but if I sit down, will she recognize me?
Because of how well it's working on Mars, I wouldn't expect it to run over you, but we could give it a try. Just
Let's
check
have
it
a go.
out.
Let's have a go. I love the words that she should.
No,
what
she will.
should happen?
She's
so what
smart.
if I really just, I mean, if I just sit here?
All right.
As I settle down for this game of interplanetary chicken, the first thing that becomes evident is that optimism is more of a tortoise than a hare. This is top speed, 4.2 centimetres a second, or just under 1 mile every 10 hours. I'd like to say it's nerve-wracking, but in all honesty, I could definitely get out of the way. As the rover drives forwards, it's constantly imaging the ground in front, building a map of the obstacles that it will need to avoid. In this case, me.
She's just taking some more images to update her nav map, and then she has to decide how to get around you. So it should be identifying, there you go. Looks like.
The thing that's impressive is that nobody's driving, so even though it doesn't look like it's driving fast, you've got to remember that she's driving across unknown terrain, making her own decisions, and this makes this rover, Perseverance, by far the fastest thing we've ever sent to the surface of any other planet. It's this unique set of skills that allows the rover to travel 200 to 300 meters every day. And if Perseverance is going to make it to La Orotava crater by the end of the week, it'll need to go flat out. At the end of day 2, I head back to the rover operations floor, where Vandy and the rover driving team should have finished the plans for the first stage of that drive. So when the rover's route has been planned, then those instructions have first of all got to be checked and amalgamated in with all the other instructions to all the instruments on the rover. So what's the arm going to do? What are the experiments going to do? Where are the cameras going to be looking? And those sequences, those commands are all put together in this meeting, which is called the CAM meeting, the Command Approval Meeting. And only when everybody's happy and all those commands have been sent to simulators, twice actually, that check that everything's going to be okay, can those commands be signed off and sent to the Deep Space Network and onwards to the rover on Mars. In here, the team are putting together the final list of instructions that will determine exactly what the rover does tomorrow. There are thousands of lines of code, and each one must be scrutinized. A single bug in the software could jeopardize the carefully plotted drive plan.
What we do after we finish on this shift is we really celebrate the effort that everybody put together, and we actually hit the gong behind me that we would love for you to do it today.
Really? Because that is a tremendous honor. Am I supposed to say something? I declare this meeting closed.
That sounds about right to me.
And with that bang of the gong, the instructions are sent off on their long journey to Mars. All being well, the rover should receive them and finally be able to start on its record-breaking journey in the morning. Perseverance has already changed the way we look at the red planet. The photos it takes can be stitched together into astonishing panoramas. Scenes that let us stand on the surface of another world. It is a stark and barren landscape, dimmer than the Earth. Because it's farther from the sun, less than half the amount of sunlight reaches the surface. But in some ways, it looks remarkably familiar. There are sand dunes and boulder fields that could have been photographed in deserts here on Earth. There are even clouds in the orange-coloured skies. And because Perseverance is the only Martian rover to carry microphones, we can hear the sounds of Mars for the first time. The whistling of the wind that stirs up the dust devils that ghost across the surface. Perseverance has even observed a solar eclipse as Mars's moon Phobos passes in front of the sun. But although there are undoubted similarities to the Earth, Mars is also a very alien world. Because it's half the diameter of our planet, gravity on the surface is just 38% as strong. And while the Earth is wet, warm and welcoming, Mars is a desolate, inhospitable place. Its dusty surface is bone dry and covered by a thin carbon dioxide atmosphere, just 1% the density of Earth's. The average temperature is minus 63 degrees Celsius. It is cold, dry, and dead. This is the world that Perseverance is exploring. Day 3, and it's an early start at JPL. Just 6 there. So coincidentally, early morning at JPL, we've just walked into Mission Control, and that bright point of light in the sky there is Venus. And just below it, you can just see this faint red pixel in the morning sky. And that's Mars. In the brightening sky, Mars is too faint for our cameras. But somewhere out there, Perseverance will hopefully have just completed the first stage of its drive. So how did the drive go yesterday?
It looks like it went well, but we really can't tell yet. The data comes down in bits and pieces, and right now we have an image that was taken in the late afternoon at about the time I would expect the drive to stop. This is looking forward, and if we look backward, we should be able to see the rover tracks. So now we're looking back the way we came. So it looks just as you would expect if it had executed its full drive.
That's interesting, actually, if you go back to that one. It's just so obvious when you say it. You can tell it's late afternoon because of the long shadows on Mars.
Yeah, it's like Earth, you know, it's not surprising.
Yeah, of course.
You can figure it out.
When the telemetry from the rover returns to Earth, it shows exactly how well the rover has fared on its drive. To start off, it follows Vandy's route through the treacherous sand patches and boulders. And then, as the autonav takes over, the rover swings north and drives itself towards La Orotava crater, covering a total distance of 204 meters and 96 centimeters. It's a great start to the journey. But after this initial success, the team are now facing an enforced change of plan. Tomorrow, the mission will temporarily lose access to the Deep Space Network. For 24 hours, they will not be able to communicate with the rover on Mars. So to keep up with the schedule, they've been forced into a risky change of strategy.
So we're making a 2-day drive plan. Because tomorrow we don't have access to the antennas that communicate with the rover, so we send 2 days worth of instructions and just let the rover do its thing, and we get a day off.
So how far would you hope to get?
About 500 meters.
Oh, really?
Yeah, that'll be a big jump.
Today they will be doing the two-salt plan.
So when you're doing your assessment today, let's make sure that everything is green and go for these activities that will be coming up.
Now, we just heard that the plan for the next 2 days is for Perseverance to do a 2-day drive. And as I speak, you can see there, at Canberra Deep Space Network, Antenna 35, there's communication upwards to MRO, that's Mars Reconnaissance Orbiter. So those are probably the instructions that are going to Perseverance to tell it what to do on that 2-day drive. As the commands hurtle their way towards Mars, I want to find out how Perseverance got to Jezero Crater. Jezero is the most dangerous location that NASA has ever tried to land a spacecraft on Mars. It is full of hazards that could be fatal to the mission. But if there's one place to come to find the engineers who could pull off this feat of precision landing, it's JPL. And this is JPL's motto, Dare Mighty Things. And JPL lives up, definitely, to that motto, as you can see from this award cabinet, the trophy cabinet. And it's just a history of space exploration. For anyone who's interested in our exploration of the universe, then this is just magnificent. You see awards for Voyager, Mars exploration rovers, the Dawn mission, Cassini, just everything. What's that one up there? That's quite ornate, isn't it? Appreciation for your support and participation in the American space experience at Disneyland. Upstairs from the trophy cabinet is the office of Al Chen, the engineer who was in charge of designing the entry, descent and landing system that would allow Perseverance to touch down in Jezero.
The scientists tell us about, the potential for life there. But when we look at it from a landing perspective, all you can see are the ways we're going to die there, all the death that's out there. It's a site unlike any other place we've tried to land on Mars. It's just got hazards all over the place. If we turn on the slope hazards here, you see the edge of the delta, which is that 60-meter-ish cliff, and then, of course, the edges of craters, and those are places we don't want to land. But, of course, that's not it. These are all the rocks that we could see from space, which means about a half-meter tall or so, or more. If you manage to encounter one of those red places, you're very likely to have a bad day.
So those blue areas there, the safe areas.
That's right.
When I look at that, it looks mainly hazard to me. Al's job was to design a system that would allow Perseverance to identify and then land in one of the safe areas near the delta.
Flight mission copies, it's go time. GDS-1, go.
But the first time his landing system could be fully tested was on February the 18th, 2021.
We are starting the straighten up and fly right maneuver.
As the spacecraft approached Mars at the end of its 6-month journey.
You are not triggered for talk. Whatever happens in the next hour and a half, you can be proud of the achievements that you've accomplished so far.
It's kind of weird to have the only test that you ever get a chance to do, in front of everybody else in the world, right? Definitely my heart was racing. I probably didn't want to know what my blood pressure was.
As the spacecraft makes its final approach, it's traveling at 20,000 kilometers per hour.
Perseverance at an altitude of about 120 kilometers from the surface of Mars.
The job of Al's entry, descent and landing system is to slow it down to walking pace by the time it reaches the surface.
We can see a little bit of that slowdown of the Perseverance entry capsule.
Because of the delay in communication with Mars, the whole process is automated. All the crew in Mission Control can do is watch and wait. They call it the 7 minutes of terror. In the first stage of the descent, the spacecraft skims across the top of the Martian atmosphere. Even though it's much thinner than the Earth's, the friction is immense, causing the spacecraft's heat shield to glow red hot.
Perseverance has just passed through the point of maximum deceleration, approximately 10 Earth Gs.
After 4 minutes, the spacecraft has slowed to 1,500 kilometres an hour. It's now just 11 kilometres above the planet's surface. Filmed with the lander's cameras, this is the actual video of the parachute deploying in the Martian atmosphere.
Heat shield has been separated.
As the heat shield falls away, the unique artificial intelligence system Al designed kicks in. Its job is to scan the ground below and identify a safe landing zone.
We have confirmation that the lander vision system has produced a valid solution.
2 kilometres above the surface, the parachute is released, and the 8 lander rockets fire up to steer the craft towards its chosen landing site. And then, the most nerve-wracking moment.
Skycam maneuver has started, about 20 meters off the surface.
The rover is lowered the last few meters on cables, touching down in a swirl of Martian dust.
Touchdown confirmed. Perseverance safely on the surface of Mars.
Where did Perseverance choose to come down?
Perseverance came down in the Cetus area, so we ended up kind of down in this region right about here. Yeah. You can see the hazards that are out there, but you can see that the area right around the rover is nice and clean. It's the parking lot we were looking for.
The first pictures taken by Perseverance on the surface showed just how precise the landing was. It had picked out a tiny area of flat ground in a landscape filled with boulders and sand dunes. But this landscape was not always so dry and dusty. It was once submerged. About 3.8 billion years ago, Jezero Crater was filled with water, forming a lake 45 kilometers across. On Earth, we always find life where there's water. If the same is true on Mars, then life could have existed in Jezero Lake at almost exactly the same time that it was evolving on Earth. With the Deep Space Network down, there will be no update from Perseverance today. But a couple of hours' drive from JPL is a unique lake called the Salton Sea. Set amongst the desert mountains, I could almost imagine the lake in Jezero Crater. I've come here to meet astrobiologist Tim Lyons. So we're sat here in the middle of a desert, very hot, very dry, no sign of rain, and yet there's this lake. So why is the lake here?
Well, the lake is here because of an engineering disaster. In 1905, an irrigation canal was breached by floodwaters from the Colorado, and it drained almost unabatedly into this basin for 2 years. Subsequent to that, it has received agricultural runoff. So the water that we're looking at now is essentially wastewater. It's a pretty nasty place, to be honest with you, and the fish are not doing very well, and the birds are correspondingly being impacted. But algae, bacteria, microbes are thriving. It's not a healthy environment, but it is teeming with life.
It's this lake's unique microbial ecosystem that makes it an ideal place for studying the origin of life on Earth and on Mars. Ah, look at these pools of colour.
And pools of life. This is the stuff. That's the warm little pond.
Yeah.
Teeming with life.
It looks just like, I'm a physicist, it just looks like some floating scum or something. Yeah,
that's one description of it, yeah.
So this is what you'd call a microbial mat.
Well, I would say that this might be a microbial mat in the making. And so this is what early Earth life was like. Some of our very best, most convincing evidence for life going back in time on Earth are microbial mats. Things like this pond that end up with these laminated concentrations, things we call stromatolites, found in places like Australia that go back convincingly to 3.5 billion years ago, and some people would argue maybe even to 3.7 billion years ago. That's very close to the window of time that is being studied in Jezero.
So if we were to imagine, 3.8 billion years ago, standing on the shores of Jezero Crater, is there any chance it may have looked like this?
Oh, absolutely. I think so. I think even a skeptic would have to admit that. And so here we're looking at the actual life that may have been present, analogous life present on Mars in Jezero 3.8, 3.7 billion years ago.
Now, I suppose you might reasonably ask, why are we so interested in the question, did life exist on a planet millions of miles away 3.5 billion years ago? I don't think actually that's a reasonable question, because the question, are we alone in the universe, is one of the most profound philosophical questions. But if you want to be more pragmatic about it, then you might be interested in how life began here. How did we come to be here on Earth? And the evidence for the origin of life on Earth has actually largely been erased, because Earth is an active world. There's plate tectonics, which take the evidence and literally take it down inside the planet. There's weathering with rain and wind and the oceans. And so there's very little evidence of what Earth was like 3.5 billion years ago. But on Mars, it's different, because Mars is a planet that's been in deep freeze for 3.5 billion years. There is no plate tectonics. There's very little weathering. So if life began on Mars, the evidence may still be there. So paradoxically, if you're interested in how we came to be here, the answer might lie up there. It's these profound questions about the origin of life that make Perseverance's mission so important. But searching for signs of ancient life on the surface of Mars isn't easy. Finding the remnants of it, and then proving that it really is evidence of life, is the rover's biggest challenge. Back at JPL, I'm meeting Luther Beagle. Hello, Luther. Hey. One of the chief scientists on the Perseverance team. It would be one of the greatest discoveries in the history of science, wouldn't it? In the history of civilization. Yes. So we're not alone in the universe. So how much would it take to convince you? I know that you can never convince a room full of scientists, not all of them.
No, we're not convincing a room full of scientists on what they had for lunch. But I don't know what that level of convincing would be. It's something that's going to take a lot of evidence and a lot of chains and a lot of different measurements to prove out.
Luther is in charge of an instrument called Sherlock. Located at the end of the rover's arm, it's a laser scanner designed to detect the faintest chemical traces that life leaves behind. And we can demonstrate its abilities with some of the most ancient evidence of life on Earth.
Life always leaves its imprint on its environments. I can show you in this particular sample here. This is a stromatolite from the Straley Pool Formation in Australia. It's about 3.5 billion years old.
I love the way you throw that away, by the way. 3.5 billion years old.
Yeah.
I mean, it just looks like a rock to me. So how would you convince me or anyone else that was biological?
Well, if I wet this rock, you can kind of see the lines a little bit better. And so So here you can really see they really come out a little
yeah.
bit better. So you can see the white layer and the black layer back and forth.
Yeah, I can see those really clearly.
Yeah.
So why does that indicate biological activity?
These particular stromatolites are curved, have different formations that could have only been created through biologic processes.
So are you looking for patterns like this on Mars?
We are looking for patterns like this on Mars as a first indication that this is either a sedimentary rock or a stromatolite, and then we have to do the next layer of analysis on those rocks.
And this is where Sherlock comes in. After scraping away the surface of the rock, it zooms in to examine it in microscopic detail, using the reflected light from lasers to detect the tiny variations in chemical composition that are left behind by living organisms.
So here you can see what a Sherlock scan, where we went in and looked at where the organic molecules on this particular rock was. The purple material here is the ancient organic material. You can see that there are lines associated with this where the basic biology then grew and died and grew and died and moved up the rock like this.
So these are literally the remains of organisms that lived potentially billions of years ago.
Potentially billions of years ago.
The great hope is that Perseverance will find similar signs of life when it reaches the delta. You must be waiting. I know that Perseverance landed and there's a lot of geology been done. You must be saying, can you just get round to the delta, please?
We do. Can we go? Can we go? Can we go? I want to go to the delta. I want to go to the delta. But we understand the geology. We're a big, giant 400-person team, so you kind of want to work together. But at the same time, can we get to the delta? Can we get to the delta? Can we stay at the delta for a while? Yeah.
So images like this are, potentially in a golden scenario, we could expect results like this in a few months.
Yeah. In months rather than years, which is nice to see the finish line.
It is a tantalizing thought that we may soon get our first hints, our first pieces of evidence that life may once have filled this crater. Day 5. After 24 hours of radio silence, contact is re-established with Perseverance on Mars. And we get our first update on the 2-day drive. Photos and telemetry show the first part of the drive has gone according to plan. The rover covering another 259 metres and 37 centimetres around the edge of the Satar sand dunes. But it seems that this is as far as the rover will be going for now.
I have no output time, so if you have any questions. Copy, officer. Thank you.
News filters through that the instructions for the second day's drive had a bug in them and were never received by the rover. To find out what went wrong, I'm off to find Deputy Mission Scientist Katie Stack-Morgan. So do you know what happened overnight when the data came down?
Yeah, so we had planned 2 days worth of driving, and that's a brand new capability for Mars rovers, being able to plan drives in a row like that. But we encountered an issue that prevented us from uplinking both of those drives and sending both of those drives to the rover.
And it's interesting to me that the problem was not on Mars. No issue on Mars at all, but it's the computer software, basically.
That's right, and these things happen all the time, and we deal with them. In a way, this is helpful to us because by giving the rover a whole day to recharge, we then fill up our batteries all the way to the top, and we can get ready to do long drives in the weekend plan. So right. Silver lining to that, to not being able to get that other drive up.
Having fallen another day behind schedule, the rover now has to travel 750 metres in just 2 days to reach La Orotava crater by the end of the week. But Perseverance isn't the only vehicle that the team has on Mars. And this week, I've also come to learn about its companion. Ingenuity, the first ever extraterrestrial helicopter. I'm fascinated by this machine because it was designed to do the seemingly impossible, to fly.
Lab. It's probably the most important space that we have as a project. So here you want to stay away from the model in the middle and the hardware along the edges.
I'm really excited to see this. It's smaller than I imagined, although the blades look to me much bigger than I'd imagined, much thicker.
That's right, yeah. So the main thing you notice is just the size of the rotor. 1.2 meters tip to tip. It's just huge, you know. And if that was on Earth with this same kind of rotor, it could lift a huge amount of mass. But on Mars, you need that just to lift this tiny little helicopter off the ground.
How much does it weigh?
1.8 kilograms. So
is that all?
That's it, yeah.
Even at 1.8 kilos, it wasn't clear that Ingenuity would be able to fly in Mars's atmosphere. On April 19th, 2021, Perseverance pointed its cameras at the helicopter as it prepared for its first flight. And millions of miles away, at JPL, its engineering team waited for news of success or failure.
This is Downlink, handing off to flight control for telemetry analysis. Engineers reporting having performed spin-up. Takeoff. Altimeter data confirmed that Ingenuity has performed its first flight of a powered aircraft to another planet.
I see you brought your logbook, which has got to be the coolest logbook.
I agree. It's pretty neat. It's called the Pilot's Logbook for Planets and Moons.
Yeah. So it's you and the Apollo astronauts, basically. That's pretty much it. I love this. So the remarks are fantastic. First powered flight by an aircraft on another world.
That's right. Yeah.
It's fantastic.
It was fun to write that.
Yeah. Climb to 3 meters, turns 96 degrees to the right. That's just wonderful. That'll go down in history, won't it? That's going to be one of those things that has a picture.
It is aviation history, you know. So it's pretty special to be part of it.
Ingenuity's place in history is assured. Initially, it was only designed to survive for 3 months and make just 5 flights. But over a year later, it was still going strong, making 20 flights, clocking up over 36 minutes total flight time and covering over 4 kilometers. But its real contribution to the mission may still be to come. If the helicopter can make it to the Delta, its ability to fly over the steep slopes and cliffs that the rover can't access will prove invaluable. But even reaching the Delta will be an enormous challenge. And just before our 7-day rover mission began, Ingenuity attempted the next flight on that journey. It's very exciting actually, because yesterday, Earth time, the helicopter flew, and we don't know what happened to it actually. The data came down last night, and this is the meeting where the engineering teams look at the data from the helicopter. see what we did. And they've allowed us, it wasn't clear they were going to do this, but they've allowed us to go into the meeting and watch as they review the engineering data from the flight.
Okay, I'll scroll up to the detailed temperature trend plots, and we can walk through those as well.
This is a make or break flight for Ingenuity. Rather than taking the long way round to the delta, it's going to attempt to take a shortcut across the treacherous Satar sand dunes. But the helicopter relies on Perseverance for its communication with Earth. And this journey will take the vehicles further apart than ever before. So a safe landing in a spot where it can maintain radio contact with the rover will be crucial.
Hazard, do you want to take us through GNC?
Sure. I'll share my screen and we see a few of our standard warnings.
As the team go through the flight data, there's a nervous wait.
This is our altimeter. We flew at a cruise altitude of 10 meters for this flight, and we flew at a cruise speed of approximately 4 meters per second. So it's looking from all of this telemetry like a good flight.
These are the pictures Ingenuity took during the flight. As it looks down at its shadow, we can track its path as it rises 10 meters into the air and traverses 370 meters to its new landing spot, from where it should be able to stay in communication with Perseverance as it drives to the delta.
And you can see our corrected SOC after accounting for solar current is around 50.4%.
What's really interesting, what really strikes me is that this helicopter was not really designed to last this long. They thought it would maybe fly 4 or 5 times. It's now like its 21st flight, and it's all working, it's recharging properly. So it's a tremendous engineering achievement. Remember, you're flying a little helicopter autonomously on the surface of another planet. And nobody's flying it. It's flying itself. If you told the 12-year-old me, who first wrote to JPL, that one day I'd be here seeing a helicopter fly on Mars, I wouldn't have believed it. But Ingenuity is just one of many reminders of how far our technology has advanced. This is a piece of history because this is the first picture ever returned of the surface of Mars by a spacecraft. It was Mariner 4, 1965. And you might see actually that it's kind of fuzzy picture. It's actually hand-drawn. These are strips of tape that came out of a printer with numbers printed on, which are the data from the cameras on Mariner 4, and they correspond to colours. And the data link was so slow that the engineers, and in particular one engineer called Richard Grum, got so bored with waiting that he went to an art shop in Pasadena, bought these crayons, these are the real ones in this box, and then sat there colouring it in so he could see the image from Mariner. Compare that to the high resolution images that we're getting back from Perseverance. Yeah, there's technology marching on. Day 6 begins. And once again, we're waiting to hear from Perseverance. Overnight, it should have received the instructions for the delayed second half of its 2-day drive. And the incoming data reveals an astonishing day of autonav driving. Perseverance has recorded the second furthest distance any Martian rover has ever travelled in a single day. 297 metres and 60 centimetres. So far this week, the rover has covered over 760 metres. But with only one day to go in our time at JPL, La Orotava crater is still nearly half a kilometre away. It will take a Herculean effort to reach there tomorrow. And while Vandy and the rover driving team build the plan for that drive, I have another appointment with Optimism in the Mars yard. Today, the engineering team are running tests on what may be the most important and ambitious system on the rover.
Starting move to contact.
All right, Greta, you can kick off coring.
All right. Yep. Sending coring in 3, 2, 1.
Perseverance, as you can see and hear, is equipped with a drill. And drills are always noisy. They're less noisy on Mars, by the way, because of the much less dense atmosphere.
We're at a depth of 3.9 millimeters out of our target 5 millimeters.
On Mars, Perseverance uses exactly the same system to collect cylinders of rock that may contain key evidence for the existence of life. So far, it's collected and stored 8 samples, with room for 30 more when it reaches the Delta. And the reason that this process is so important is that one day these samples will hopefully be brought back to Earth. Minnie Wadwa is the science lead for the mission that will return the Martian rocks to this planet. Why is it so important to bring the samples back to Earth? Because I suppose naively, you say we've got this tremendously sophisticated robot, it's got the samples, why doesn't it just look for signs of life itself?
This is an incredible machine, but the kinds of analyses that we want to be able to do with the samples is going to require really the best and most sophisticated instrumentation that you have available on the Earth, and it's just not possible on a small rover like that. Yeah. The other factor is that we want to be able to reproduce results. I mean, can you imagine what it would be like if somebody actually found evidence of past life in these samples? We'd want to verify those results, and we'd want to verify them in independent laboratories. That's not something you can do with a with a remote laboratory on Mars. You've got to bring them back here so that the best scientists and the best labs can really have at it.
Yeah, I suppose it is an example of extraordinary claims require extraordinary evidence, isn't it?
Exactly.
Bringing the samples back to Earth will not be a trivial task. To do it, engineers have designed a mission unlike anything I've ever seen. It's called Mars Sample Return. The Mars Sample Return mission sounds really simple as a concept, right? All you've got to do is get some samples from the surface of Mars and bring them back to Earth. But actually, when you hear the engineering solution, how to do that, it sounds fantastical. So there are 2 missions that fly to Mars. One is the so-called Fetch rover, which is a little rover, which is going to land on the surface of Mars, and it's going to drive around and it's going to pick up the samples, bring them back to an ascent vehicle, which is the thing that's going to launch those samples into orbit. And then the sample thing itself detaches away. And it's something about a basketball size, maybe a bit bigger. And then another mission comes from Earth, and it has to locate this thing that's in orbit somewhere around Mars, and then it has to kind of go and grab it in space, and then when it gets to Earth, it'll detach with this precious cargo in it, will enter the Earth's atmosphere, no rockets, no parachutes. It will just impact into the sand somewhere in Utah, and then they'll go and find it and bring it back into laboratories. And that, believe it or not, is the simplest and safest engineering solution to bringing something about that big, filled with samples from Mars, back to Earth. Now, all that might sound like science fiction, but actually it's going to have to become science facts pretty soon, because the first bit of the sample return mission is supposed to launch in 2026, which is only, about 4 years away. They're preparing for it now. In fact, up there, see that tower? That's the test bed for the dropping the capsule that returns those samples to Earth to see when it hits the ground if it survives. So it is not an exaggeration to say, as I'm going to say it, that I think the best engineers in the world are working on this project. Here at JPL, development is well underway. They're already testing the systems that will launch the rocket from the surface of Mars, and the capsule that will crash into the Utah desert. If all goes to plan, the samples collected on Mars could be returned to Earth by as early as 2031. It's undoubtedly a risky mission. But there may also be risks when the Martian rocks are safely back on Earth. And that's what I want to investigate on my last day at JPL. Bringing Martian samples back to Earth is going to be vital if we're ever going to prove that there was life on Mars. But there is an outside possibility that those samples could also cause a problem for life on Earth.
Welcome.
I mean, I've got to say there are badges of every mission that I grew up with here. So what's this room?
This is the spacecraft assembly facility. It's where all of the magic happens. Every single spacecraft built at JPL was assembled in this room.
Mugega Cooper is one of the people whose job it is to make sure that our planet stays safe. So you have one of the best job titles, I think, which is Planetary Protection Lead for Mars 2020. So what is planetary protection?
Planetary protection is twofold. Right? We have to make sure that as we send spacecraft out into the solar system, whether to planets, moons, or asteroids, we have to make sure that we don't spread our contaminants to those places of interest, especially if it could harbor life. And the flip side, if we were to bring samples back to our own planet, we have to make sure our planet is protected from anything that might be harmful out there.
So are we worried about microbes from Mars?
Yeah, in fact, the assumption is to handle it as if it's hazardous until proven otherwise. The level of precaution that is going to be taken with these samples is that of a hazardous material.
So when we bring the samples back, so we've heard this audacious sort of idea. I mean, Mars sample return is terrifying, right, from an engineering perspective. But essentially, you're going to crash it into Utah, right?
A controlled crash.
I know that's not the language you use. There's going to be a controlled descent.
There we go.
Without
Perfect.
parachutes into Utah. So what is the procedure from then on? So you have this capsule, sealed capsule, in the desert. What happens to it?
The goal in general is to take that capsule, bring it to a facility that is unlike any facility that exists today on our planet, to safely contain anything that might be in that sample while we open it up, extract the samples, and interrogate it scientifically.
So we will build a biolab like no other.
Exactly.
Essentially.
Yeah.
For the Martian samples, NASA is planning on creating the most biosecure laboratory ever built. More secure than the labs like these that handle lethal diseases like Ebola and smallpox. But while taking all possible precautions is definitely the right thing to do, it's probably too late to protect us from Martian contamination. When we speak about planetary protection, that sort of gives the sense that Mars and Earth are completely isolated from each other. But that's certainly not the case, because this is a piece of Mars. It's from a Martian meteorite that fell in Nigeria in 1962. Now that raises an interesting possibility, because if rocks can be transferred from Mars to Earth, and actually about 500 kilograms of Mars floats down onto the Earth every year, then maybe so can life. The idea that life could migrate between the planets may sound incredible. But there are scientists who believe it's possible that life could have arisen on Earth and been carried to Mars on a meteorite. And it's also possible that life began on Mars and was transported to the Earth. Now, we don't know if that happened. But a key step towards finding out would be to find traces of life on Mars. And it certainly adds an extra dimension to Perseverance's mission. As our week at JPL comes to a close, we get a final update from Perseverance. It's still trundling towards La Orotava. The telemetry showing it's completed another 240 meters and 70 centimeters of auto-nav driving. It's 200 meters short of the crater, but it's still been a remarkable week. So are you happy with the way the rover's performed? Because I know that this was a big week for you, making this transition from the first scientific campaign to the long drive around to the Delta.
Yes, this was a big week for the mission and a major turning point. We've been moving our way slowly through the crater floor, but now with this goal of getting to the Delta as quickly as possible, we're really flexing the rover's legs, so to speak, and trying out a new mode of operation, and that led to some unexpected surprises for us.
Yeah, that's what I find really interesting. It's what I've learned, is that even though you know this rover well now, the moment you ask it to do something slightly different, then you learn a lot more about the rover. But the way it behaves on Mars and on that terrain can always surprise us. This is the rover's eye view of the journey it's made this week. Even with the hiccups, the drill stuck in a rock and the day lost to a software error, Perseverance has still covered over 1 kilometre. At 1,003 metres, it's the furthest any planetary rover has ever travelled in such a short space of time. JPL's motto is "Dare Mighty Things." And after spending a week watching Perseverance drive over the surface of Mars in search of alien life, my overriding impression is that that is entirely appropriate. The sheer engineering excellence, the attention to detail, the teamwork required to do that is nothing short of astounding. It turns out that if we try to answer the most profound questions, to acquire new knowledge about the universe, not because it's useful in some sense, but just because we want to know, brings out the best in us. But the end of our week at JPL is not the end of the story. Several weeks later, Ingenuity is still flying. It's now clocked up almost an hour of flight time and is still sending back remarkable aerial photographs, including these images of the mission's parachute and protective back shell that were last seen as they were jettisoned on the descent onto the Martian surface. Ingenuity made it to the Delta in another 7 hops across the Satar sand dunes. And the rover kept on driving, covering the remaining 4 kilometres in just 31 days, capturing some truly wonderful pictures as it approached the steep scarps of the delta. The rover and helicopter are already investigating the delta's sedimentary rocks and have begun searching them for the faint signs of ancient life. Whatever Perseverance finds, it will tell us something important about ourselves. I think there are three possibilities for what Perseverance might find on Mars. One, which sounds like the most disappointing possibility, is it seems no sign of life at all. If we establish that there was water in Jezero Crater, all the conditions were right, geological activity, all the right ingredients, and yet life did not begin, then that may be telling us that we're alone, certainly in our neighborhood. The second possibility is that we find life, but the life is very similar to life here on Earth. It'd be wonderful. We'd know that there are 2 planets in our solar system that are living worlds, but it might suggest that there was only one Genesis in our solar system. But we know that material moves from Mars to Earth. We have Martian meteorites here, and from Earth to Mars. And so then, I suppose the story becomes, where did life begin? It is certainly possible that life began on Mars and was transferred here to Earth. I suppose in that sense, we're Martians. What a discovery that would be. The third possibility is that we find signs that life existed on Mars, and that life is very different to the life we see here on Earth, has a different biochemistry. There was a different genesis. That would mean that life began separately in 2 places in our solar system. And that will tell us a tremendous amount, because it will tell us that we can assume that wherever the conditions are right, life begins. That will be a profound discovery. It will change the way we think of our universe, because it will mean that we are in a living universe. It should change the way you look at those points of light in the sky. Many of them, most of them, have planets around them, and I think we'll be able to assume that a good number of them are living worlds.
From tiny invisible worlds to things so vast they blow our minds, Secrets of Size, watch now on BBC iPlayer. And Professor Brian Cox and Robin Ince take an irreverent look at the world through scientists' eyes, The Infinite Monkey Cage. Listen now on BBC Sounds.